All right, so here we go. For those of you who weren't in class or just need a reminder, we talked about the board a little bit and sort of the fact that Monopoly is a dynamic game where people have to do expected values about investing in a property and how much they're going to make and whether they should put houses on and whether you should trade one Monopoly for another. And that can get fairly complicated in the full-on analysis. It's doable. But what we're going to do is we're going to do an expected value calculation, which we have over here to start with, but I'm going to break this down. You see each one, the price, the rent, all of these are from the cards. The price per house, the rent for one house, the rent for two houses, et cetera, et cetera, et cetera. And then over here we have sort of a fake expected value. It's just per time around the board or per time you get paid, right? What percentage is that house? So if we look at this, what this figure is, it's E2 over F2. So it's the price or F2 over E2. So if you got paid $10 in rent, every time you get paid rent, then it would give you 20 cents or to 20% of the, so you'd have to hit it 5 times to get it to come back. Now we're going to use that as a proxy for expected value, and then we'll actually do expected value calculation, but this will just make it a little simpler. And so what I did from your sheet, you'll go to the expected value sheet and copy all of these down to the hotel, to the blue. You'll do a Control C and then come over and create a new and a Control V to paste it and get rid of these cells like this, delete. And I'm going to bounce over to the one that says blue here because I've put some other things in it that I want. And I'll walk through them. So we have our payoffs out here. First thing I wanted to talk about a little bit was marginal value, right? Marginal revenue. Okay, because there's a bunch of sites out there that say your income and it's should be revenue, but that's okay. So the marginal revenue by a house is going to be F2 minus D2. And then the marginal revenue for the second house equals the rent on the second house minus the rent you would get with only one house. And we can copy that over. And then we can go ahead and copy that down to, and that gives us sort of all our marginal revenues. The highest marginal revenue is moving from 2 houses to 3 houses on Connecticut. I'm just pasting it here to make it easier to see. Stretch it out there. And so these are the, so you can see each of those marginal revenues. Now they don't include the marginal cost because you'd have to, you know, in this one you go up $24, it's minus 50, but that's the marginal revenue and marginal cost calculations. You only have to pay the cost once. Are a little trickier, and we'll get to that in a little bit. But so here we're going to not worry about this rent because that's sort of sunk. And so the value of one house, the increased value of one house is 0.6, 0.8, 0.9. And those are the ones we saw back here on the expected value. Down here was the 0.6, and that was F4 over E4. But when I copied it, now these are just the actual values that were there. And if we want to play a game where we put in ones and zeros here, we're going to have a decision matrix where we could have 1, 1, 1, and then everything else would have to be 0, right? So because you can only have, right, if you have one house on if you have one house here, you can't have two houses, right? If you have one house on Oriental, you can't have two houses. If you have two houses, you can't have one house. So we're going to create a. And this is L5, which is where we want it to be. And so I'm going to move these down because my formulas are slightly different. So I put them here. Sorry, I'm going to fix that. We'll go through the formulas. So I just moved it down so I have a sheet there. If I wanted to put headers in, I can. So if we put one here, we would have to take away one there and one there because it's two houses. And if we only have three houses, this makes sense. We only have three houses. So then what we want to do here is calculate our payoff, right? And so we'll put the ones back here to make sure it's working and get rid of the one there. And so our payoff is going to equal 0.6. If this is our investment times that one, plus times plus 0.8 times the one. All right. So we have L2 times L6, L3 times L7, and L4 times L8. And I missed something there, so. And that's ends up being 2 because that's 0.6 plus 0.6 plus 0.8. All right, well, there's a big blank spot. I'm going to cut that out. All right, and so you see that, so we now have these values and this is our payoff, so we're gonna copy that all the way across and that's our payoff. So you see that it's 2. If we decided that we wanted to move 2 of the houses over someplace else, so like we wanted to put 0 and 0 and 2, then you see our payoff would go up to 2.6. So we could sit here and mess around with this to see which combinations would actually give us the highest. So I'm going to go back to my original for no other reason than I want to make sure this formula works when I type in the number of houses. So the number of houses is going to equal that plus that plus that, right, which is 3 houses. What is wrong with my font color? All right, so now that, and this one would be, and we'll just make this so the formula remains the same, times 1. And we'll copy that all the way across and then change these formulas. That's going to be 2. That's going to be 3. That's going to be 4. And that's going to be 5. It's again a shorthand. We should do hotel separately, but it's the same with 5 houses in terms of cost. So our payoff is 2. Our 3 houses are the total. And I'm going to click save here. Now we can do something called the solver. It's an optimal control problem. What is our optimal number that we would put in there? And if you don't have, if you go to data, if you go to data, you should see solver over here. If you don't see solver over there, you have to go to file, options, add-ins, go, and turn on solver. For Mac people, I'm going to get canceled because it's already. For Mac people, it's over here in tools, add-ins, and then you click solver. So I'm going to go to data and click my solver. And you see it's already filled out here, but it's all wrong. So I'm just going to get rid of all these. So we have a blank solver cell. Okay, and then I will close it. And super happiness, we can fix this quite easily in our solver. So let me go back to data and solver. And now it's empty. So what we want is our payoff, which is 2. Our objective is our payoff, yeah, which is Q9 in this case. And then by changing the cells, we're going to click just all of these decision cells. And then we need a constraint. I missed that. I mucked with it. And then we need to add a constraint that all 3 of these are less than or equal to 1. Q6 to Q8 are less than or equal to 1. And that's because you can only have 1 or 0 on any property. So that will help us make sure that's there. Then we need another constraint that we're going to make this less than the total number of houses. So we'll add that Q10 is less than or equal to, and we'll start off with 3 houses, why not? And we'll say, okay, so that's there. And then we need to add one more. Nah, we'll just finish with that. And then we'll add the other constraint after we make a little mistake here. I'm going to click cancel. And this here, there's only one house is Q8. So these are, something got messed up here, and this should be equal sum. Oops. I'm going to close it. And okay. And okay. So the objective cell still needs to be the payoff cell. And then we'll click solve and cancel. And that, because these constraints aren't correct. This needs to be the sum of those. And we'll copy that down. So it's the sum of those. All right. And we'll go back to our solver. And now it looks like everything is correct, I think. And we will go ahead and click solve and it will spin for a minute. And it's telling us that we shouldn't get anything. And this is wrong. And I'm going to put cancel because something's not right here. All right, let's try again. And our Q9 is our payoff. That's correct. And Q10 is less than 30. That should be 3. And Q6 to Q8. Are less than 1, and we go to solve. And the solver solution leaves it at 1 and 1 and 1, and we say, okay, that shouldn't be correct. So something's wrong with our payoff function. Or is it? Maybe that is the, so what if we went, oh yeah, well, we can't, we're 3 houses, right? We could go to a 2 and 1. So let's see if we put, this one would make the most sense if we put 1 there and went to 0 here and 0 there is 1.6. So it actually is the 1, 1, 1. That is our highest payoff under this payoff matrix. It might not work when we do it the other way. So it really was 1, 1 and 1. That was my serious weirdness there. So let's go ahead and go back to our data, our solver, except let's now change that from less than 3 to less than 7. What if we're going to put 7 houses and then solve? And oh, okay, it's putting partial houses, which we don't like, right? We shouldn't allow partial houses, so we need to add one more constraint that those have to be integer number of houses. All right, so I'm going to do cancel, go back to the solver, and we're going to add one more constraint. And we are going to select all of our choice cells here again, which is our L6 through P8. And here we're going to select integer. And we will add that. And then, okay. Cancel, did we get it there? Yeah, so there it is. We have our integer constraint there now. And so we can go ahead and solve it. And now we get 2 here and 1 there. So our integer constraints, we have a payoff of 4.4. Could we move things around and get a better payoff? Well, you can play with it and see if you can, right? If we had What if we put the 2 here and the 1 there? What will we get? I'm going to say, okay, so we can play with that. What if we went with 1? Oh. What if we went with 1, 0, and 0, and 0, 1, and 1? All right, that gives us 4.4 payoff on the 7. And what if we go ahead? What if we what was that? I should have written it down. We'll look at our and solve it. And okay. And it's 4.4. It didn't matter which one of those there. So if solver stops at the first maximum, if there's more than one maxima, then it doesn't bounce around and give you the different choices. We will go ahead and go to data and solver again. And so, except this time, 3 and 3 is 6 and 7, right? We are going to change that. What would happen if we had 10? All right, and so now when we have 10 houses, we have the most expensive payoff that we can get in a hotel. It doesn't work to move these this time. And we can try that if we move this to, so right, it's 5.85, put 1 there and 0 there. Right, and 1 and 0. Right, our payoff drops down to 5.8. So you can see that the algorithm works pretty well and it finds sort of the optimal investments for us. And we're going to end this here. In class, we'll do something a little different where we look at a bunch of other formulas. And I'm going to preview those for you in just a minute. Ooh, we'll make them bright red. So there you go. So we have another series here that you will see and we will walk through, which have formulas that allow us to calculate the actual expected values where we, these were some proxies to make it easier and make the formulas simpler. These formulas are much more difficult. We'll get into those. We might do it Wednesday, but we'll get into it and show you these one more time. I just wanted to show you solver and to show you how quickly you can set up a solver matrix. I wanted to show you this if somebody says these aren't the real expected values. You need to take account of things like all right, you need to take account of like how many rounds are going to be, probability of landing on a cell. This number is not quite correct. There's a great website that talks about and shows all the different probabilities you could have depending on whether people stay in jail a long time or not. But this was just a pro forma to show you that we could do it and that it works and that we can use the Excel solver to solve really important problems like the expected value of an investment in Monopoly. 3 houses, better than you think. All right, certainly has some of the best marginals out there. In the sheet that I uploaded, it also does it for the greens. And this side of about 10 landings. A lot of them are kind of negative if you get down to the actual probabilities of hitting stuff because people sit in jail and et cetera, et cetera, et cetera. It's about 0.028. And you'll see that the profitability changes. So I'll show you how to use those formulas and stuff as we move on in the class.